table, or n increases, this is our principal quantum number, and if this results in more orbitals, which results in higher shielding. You have more orbitals in the inside shielding that are shielding the valence electrons. Okay. Going across from left to right, what time is it now?
11:32.
Okay. Z increases pulling electrons closer. So this is going to pull electrons closer together. I think after this it's going to be good to show the periodic table because it's going to show the trend really nicely. As Z increases, shielding decreases. Okay, so let's spin this. Yeah, turn the light. Oh, yeah, let's make it dark. So let's spin this sucker around. So here is a really nice periodic table that shows relative sizes of elements. And we're just going to ignore the cations for now. We're going to talk about that in a second. And so, because shielding is really high on this side, the valence electrons do not feel that pull from the nucleus, that proton pull to shrink in the electrons closer. So the valence shell becomes larger. As you move in this direction, you'll notice that they get smaller because shielding is decreasing. So our elements become larger as you go down, and they become smaller as you go to the right of the periodic table, where we have fluorine, which is a very, very, very tiny little atom when it's not charged. So we're not talking about cations or anions, we're just talking about the neutral species for each of these elements. I really should print something out like that. That's a good one. Okay. All right. Now let's talk about cations and anion size. And let's get a piece of paper so that we can gloss this. So now we're going to talk about the sizes of cations and anions as you add electrons. So as a metal becomes a cation, by losing electrons, there is less electron-electron repulsion, allowing for the radius to contract and therefore become smaller. So as you lose these electrons, it becomes more positively charged, which means that the nucleus can pull in those electrons closer to itself, meaning that the radii for that ion is going to become smaller. So if we go back to the, sorry, I'm like going back and forth. So if we go back to this example here, let's look at what's a really, really good one. Let's look at sodium. So sodium, what are these values I assume are in picometers? Sodium on its own without losing an electron is 1.86 picometers in, I'm not sure if it's going to be radial distance. I'm pretty sure it's radial distance. We'll just say it's radial distance. When it loses an electron, the pull from the nucleus is going to be strong enough to shrink it. So it goes from 1.86 picometers to 0.95 picometers. And that trend is true for all the cations. Chromium goes from 1.25 to 0.84 where it becomes chromium 2 plus and such. So the higher the charge, the positive charge, the smaller the atom becomes. The opposite is true for our nonmetals. As a nonmetal becomes an anion, by gaining an electron, there's more electron-electron repulsion, allowing the radius to expand and become larger. So if we go back one more time to our periodic table, let's look at fluorine. Fluorine is a really, really drastic example. We start at 0.64 for neutral fluorine picometers. When it gains an electron to become like neon, it goes from 0.64 to 1.36 picometers. It like doubles its size because of,
Zoom in on
yeah,
it.
go ahead and zoom in on that. Because of this electron-electron repulsion. Right. Now there's an energy involved with adding an electron and removing an electron. For removing an electron, this is known as ionization energy. It is the energy needed to strip away an electron. So if we start with a metal, we're going to oxidize this metal by removing an electron. We get a metal plus an electron. The ionization energy follows opposite trend as radius because it increases up and to the right of the periodic table. So if we look at the periodic table, the ionization, the energy required to kick off an electron increases as we go in this direction. And that makes sense. All our metals, they like to get rid of their electrons. So they have the energy requirement to kick one off is going to be lower than for a non-metal who wants to gain electrons. They want to gain electrons. So they're even more stubborn to hold onto the electrons they already have because that's going to take them further away from our noble gas configuration. So the energy required to remove an electron from lithium is going to be smaller than for, let's say, fluorine. Fluorine's energy is going to be way, way larger. As shielding increases, the outermost electrons, valence electrons, are more loosely bound and therefore easily removed. Remember, as it billows up in size, the valence electrons are further away from the nucleus, therefore they're easier to pluck off. So let's talk about some trends on the periodic table. I unfortunately did not print this out. This is from your textbook. This shows ionization energies, a trend for the periodic table itself. You'll see that we're going up and down a lot. We're going to talk about a couple trends right here. So if we talk about, let's say, the ionization energy from going from lithium to beryllium, there's a big jump. We're going from 500 kilojoules per mole to about 1,000 kilojoules per mole. This is expected because the 2s electron orbital, the electrons in the 2s orbital do not shield each other. So the energy required to remove both electrons from this beryllium is going to be higher in energy. If you go from beryllium to boron, the 2s orbital is shielding our p orbital, and because of this, the p orbital is going to be further away and it's going to be easier to pluck off that electron, so the energy required to pluck off that electron from boron is going to be lower. The ionization drop from nitrogen and oxygen can be described if we draw the actual orbital diagram. So I'm going to take this off for a second. We're going to do the configuration for just the 2p configuration for nitrogen and for oxygen. Zoom out. This is 2p for, that's right, nitrogen, 2, 3, 2p for oxygen. So if we look at the periodic table, let's pull this up again. Nitrogen is going to have 3 electrons in its p orbital, so we're going to put 3 separated. Remember, we don't put 1, 2, 3. We separate them out because of Hund's rule. And then our oxygen is going to be 1, 2, 3, 4. So we're going to have 1, 2, 3, 4. So you'll notice, let's go back to our table. Oxygen has a lower ionization energy than nitrogen. The reason for this is this pairing energy, these 2 electrons are paired in the same orbital. The electron-electron repulsion of this is strong enough that this electron doesn't want to be close to that other electron, so it's higher in energy, so it's going to be easier to pluck off. This explains the reason why we have this dip from N to O. Side. Okay. You'll notice again as we move from as we move left to right of the periodic table, our ionization energy is going to be increasing. So we start with lithium in one row, and when we get to neon, because neon's already in a noble gas configuration, it definitely doesn't want to release its electron, so its ionization energy is going to be really high. And the half-filled shell half-filled shell electron configurations are going to be more stable again than other configurations. Therefore, they're going to be more stable. It's going to be harder to remove those electrons, and that describes some of these discrepancies that you see for the transition levels. So, as I said, this is just showing exposure to you guys. All right. So in order to determine, to calculate ionization energy, we use the Rydberg equation. So this is, this out a little bit. Keep losing names. Sorry, calculating ionization energy. So we're going to go back to our handy-dandy Rydberg equation. Delta E is R sub H 1 over n squared of I minus 1 over n squared final times E squared. So if we have an electron in a shell that we completely remove so that it is no longer on that atom, we're going to say that the shell that it's in its final position is going to be so far away that it's approaching infinity. So if our n sub f approaches infinity, then if this number is really big, if I were to plug in, let's say, a billion, 1 over a billion is basically 0. So our equation simplifies to ionization energy, because we're ionizing an electron. We're not moving shell to shell. We're just removing it completely. R sub H 1 over n squared I times E squared. This would just be the equation that you would use to calculate ionization energy for removing an electron completely. Okay. So this is one method you could do it. A more accurate method you would use is another method to determine ionization energy is to add up tabulated values for a given element. That is the ionization energy removing the first electron, the ionization energy removing the second electron, third, and so on. This method is more accurate since these ionization energy values are experimentally determined. So there's tables and tables of the energy required to remove an electron from an element. And so if we were, let's do this example, what is the total ionization energy required to take aluminum from aluminum 0 to aluminum 3 plus? You would be given a table of ionization energies to remove the first electron, which is 580 kilojoules per mole, the second electron, 1815, and then finally the third electron. And all you would really do is just add those values together. Were you looking for plastic?
Blank paper.
I have a bunch of blank paper. So by adding these three values up, I1 plus I2 plus I3, this gives me the total ionization energy to go from aluminum 0 to aluminum 3 plus. So I'm just going to add these values up. 580 plus 1815. Oh. 1815 plus 2740. And adding these three gives us a ionization energy of 5,135 kilojoules per mole. So if I had a mole of aluminum that I wanted to take up to aluminum 3 plus, I have to give it this amount of energy in order to oxidize it into aluminum 3 plus. What time is it?
11:45.
Hey, that. All right. So you might be asked a question for ionization energies, and then the question will have a table of information, and then you would use that table to determine what the ionization energy is required to go from oxidation state to oxidation state. The opposite. So we were talking about ionization energy. We're going to talk about electron affinity. Electron affinity is when an atom gains an electron, generally nonmetals, so elements on the right side of the periodic table, the energy required to add this electron is electron affinity. So this is going to be the opposite of removing an electron. We're going to take a nonmetal, we're going to add an electron, it's going to become a negatively charged ion, an anion. The energy to add this electron is negative and increases negatively up and to the right in the periodic table. So this electron affinity is going to be increasing as we go in this direction. So that way. This is in conjunction with electronegativity, which is the desire for an atom to gain an electron and is related to the ionization energy, which is greater than 0, and electron affinity, which we just said is less than 0. Electronegativity also, along with electron affinity, increases from up to the right of the periodic table. So electron affinity and electronegativity increase as we go from here all the way to here. Fluorine being the most electronegative element in the entire periodic table. That's it. That is all of it, man. So, with that being said, if they cancel classes again on Friday, I intend on recording the review session. I will do the same thing that I did last time, where I wrote a bunch of examples and I'll work through the examples for you guys. There's going to be gas examples, there's going to be electron examples, and that's pretty much it. Remember, the test is going to again cover just the section on electrons and the section on gases. You will not be quizzed on any of the new stuff that I just went over today. Did I miss anything? I don't think so. Okay. Hopefully this video comes to you guys easily. Thanks, Dr. Henry, for letting me do this. This works out really great. Bye.